Hello, hello. This is Martha, and in this video I'm going to attempt to walk through a proof proving that the sample variance is an unbiased estimator of the population variance. Now before we jump in, we're just going to have a quick review of unbiased versus consistent and some setup before the proof. So unbiased versus consistent is a very broad overview, but when something is unbiased, when a measure is unbiased, we say the expected is equivalent to what we get in that population. So the sample is equivalent to the population. So if we have, let's say, a nice population that looks like this, and we have a true population mean here, which we're just going to, for some population measure, that is going to be the same as our expected. So that's unbiased. Consistent is a little bit different. We're working towards, we're interested in the true population parameter. But a measure is said to be consistent if, as the n, or our sample size increases, that estimator, that estimation, moves towards the parameter. So visually it might look like this. Let's say that we have our true population measure over here. Just for simplicity, we're going to do mean. And our first sample, let's say, it's a sample of 50. That's our expected, our n equals 50. Now, if we take increasingly larger sample sizes, that measure moves closer. So we've taken 3 sample sizes and we're getting closer and closer to that true population mean. And that is when a measure is consistent. So that's the difference between unbiased and consistent. There's a few things that I'm going to set up before the proof just as givens and knowns, and these will be on a reference box in the next slide. So the first thing is that the expectation of the summations is of a random variable is equivalent to the expectation of the summations is the same as the summations of the expectations of a random variable. And kind of along that same principle, if we have a constant, if we have our expectation, then there's a constant times our variable. Because it's a constant, we can say that it's the same as the constant times the expectation of that variable. Now we're going to go with the variance. Now if we remember, the variance of a random variable is the variance of x squared, that variable squared, or the expectation of that variable squared, minus the expectation squared. And this is the same for sample and for the population. Now we can also mathematically switch this around because in the proof we want to know the expectation of the squared variable, and that is equivalent to the variance of that variable plus the expectation that variable squared. Trying to get a little bit better at my notation. Taking it one step further, we've got the expectation of that variable, and the squared should be out here, is equivalent to sigma squared plus mu squared. Now the sample is very similar. The only difference is that because it's a sample, our variance is sigma squared over n. Additionally, for our proof, we want to remember that our x bar, our sample, it is the summation of x, the variable of all the variables divided by n. Now we can multiply each side by n to get that the summation of that variable is equivalent to x bar times n. The last thing that we need to remember is that if we're summing something up from I equals 1 to n, we're going to take that sum n times. And so we'll be using those in the proof. Our sample standard deviation is the same as the population standard deviation. If the measure is unbiased, it should come out that way. And on the left-hand side, we've got a nice reference box of all the things that we covered in the previous slide, and the setup and the formulas. I just like to keep those on hand. So let x sub 1, x sub 2, all the way to x sub n be independent observations from a population with a mean mu and variance sigma squared. Now, to keep this a little bit neater, I remember that this summation is I equals 1 all the way to n. To keep things a little bit cleaner, I'm not going to write that out with every step, but just remember that that is part of it. So let's jump in. We're going to start off with our formula for the expectation of the sample standard deviation. And because this n minus 1 is a constant, I've kind of moved it outside. So that frees us up to look at the summation of x sub I minus x bar squared. So what we're going to do is we're going to first FOIL that. And if we remember the old foiling, we've got a minus b squared, we're going to end up with a squared minus 2ab plus b squared. So if we follow that same pattern, our next step carries us to that expectation of the summation of x sub I squared minus, we've got the 2 summation xi x bar plus that summation again of x bar squared. Now this second part, this x bar and this 2, they're constants, so we're going to pull them out. Again, the summation is going to be the n number of times that we sum it up. So we can write this next as we've got the expectation of the summation. Remember that's I equals n to 1 to x bar summation xi plus n x bar squared. Now if we go over here, we've got this. We've got the summation of x sub I that we can then plug in. So if we do that, we get that the expectation, again summation, I equals 1 to n, x squared minus 2x bar, nx bar is equivalent to the xi, plus nx bar squared. Now we've got 2n x bar and then n x bar squared. So if we carry this through, we're going to end up with, we've got negative 2 plus 1. We're going to have that our expectation summation I equals n to 1 xi squared minus n x bar squared. Here we go. All right, we're making pretty good progress here. So the next thing that we're going to do is then we're going to distribute this expected through. So that carries us to the expectation of that summary Remember, it's I equals 1 to n of x sub I squared. And then we've got minus that expectation of nx bar squared. And this is where the work that we did previously really helps us out. Because if we look for the expectation of our variable squared over here, we can, at this point, use that this is sigma squared plus our mu squared. Now over in the second part where we've got minus that expectation, our n is a constant so we can move it out. So we've got minus n times our expected for our sample squared is equivalent to sigma squared over n plus mu squared. So distributing and getting everything worked out, what we end up with is n sigma squared plus n mu squared, or n comes from our summation here, minus sigma squared minus n mu squared. And so this, we're getting there. These are going to cancel out. And what we're left with is sigma squared n minus sigma squared, or if we carry it just a little bit further, we've got sigma squared times n minus 1. Now, if you remember, we've just been working the top part of our formula that we started with up here. So let's go ahead and put everything back in, and we get that 1 over n minus 1 times this whole big expectation up here, which we worked out to be sigma squared, times n minus 1. Our n minus 1's cancel out, and we're left with that equals sigma squared. And this is one way to do that proof. All right, so this has been one way to prove that our estimation of sample standard deviation is unbiased and is equivalent to the population standard deviation. There are other ways to do this proof. If you would like to send me others to work through, I would love to hear it.